Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. There was last piece, I think, in the previous lecture. We were talking about contextual embeddings. Okay? Can one of you or any of you tell me why we need actually contextual embeddings, and what do we mean by contextual embeddings? Yes.
Because we want for the same word to have many embeddings.
Why?
On the context of the word.
Okay. So depending on the context of the word, and because some words have different senses, okay, or different meanings, so we would like to have the embeddings to be different within different contexts or for different meanings. So far, what we learned is that we can train embeddings, or we can get embeddings that are static, they are fixed. Okay, given a word, regardless of its new context, you will get the same embeddings. Just a lookup table after we train these embeddings. So we need what we call contextual word embeddings, and we will briefly study one of the really nice examples, which is called Elmo. Before we do that, Elmo actually is based on an idea of learning or training language models using neural networks. So there is a type of neural networks called recurrent neural networks, in which the network takes the input in sequence. So it takes one input at a time. So if I have a sentence, then one word will enter the network, will be an input at every step. Okay, that type of networks was used to learn a language model. We discussed, or we covered language models before, right? So what do you mean by learning a language model in general? So what is a language model? Yes?
Is it the probability distribution?
Yes, so that's a distribution over words, and we use that to know to compute probabilities, right? Probabilities of seeing one word given maybe the previous word or given the previous two words, right? So that's what we mean by learning a language model. Given some sequence of words, what is the probability of seeing a specific word after them? Okay, so that's the general problem of language learning, modeling, and that's what we learn. Okay, when we say that we want to learn a language model. Now, how can we do that using a neural network? Actually, the example here is using recurrent neural network. So the input initially will be nothing, and we want to train the network to predict the next word. Okay, so here we have just one example. Cats average 15 hours of sleep a day. Okay, so this is like a training example now. So we want the network to predict from the beginning that there will be cats. Of course, this is very hard. But after cats, I want to predict average, and then after average, I want to predict 15, and so on. Okay, so that's in the training phase. I want to learn the weights or the parameters of the network so that given a sequence of words, the network should correctly predict the next word. Okay, so in the beginning, I will get a prediction from the network, and this prediction will be like a classification. Will be like a probability distribution over all words to tell me which one the one with the highest probability will be the one that the network predicts. Okay, so here I want probability of cats to be the highest because now the first word is cats. Okay, now assuming that the next word is cats, the recurrent neural network doesn't only work with the input, with the new input. It takes the current state also as an input to it. Okay, so the current state is defined by some weights in the hidden layers of the network. Don't worry much about where exactly, but it is a state of the network now, given what the network saw already. Okay, so the input now will be the hidden state or the current state from the previous step and the new word. So the new word now is cats, given the state of the previous step, okay, which should indicate somehow the whole sequence of the words that were seen before, okay, or the context so far, okay, but just the left context. Now with that, I want the network to predict a new word, which should be, if the network is doing its job correctly, should be average, okay, so that will give us from the network the probability of seeing average given cats. If we repeat that with every word, the next word, the hidden state of the network will be input. By the way, this is the same network. That's why it's called the recurrent. Okay, so the same network will take always two inputs, one word and the current state of the network. Okay, that's why it's called the recurrent. But here we are folding it out over time. But it's just one network here. It's not multiple, but just to show it, we are folding it out over time. So now the input is the hidden state from the previous word, and the new word is average, and I want the network to predict that the next one will be 15. Okay, so that's in training. That's in training. So we'll continue with that until we reach the last word. And with the last word, day, I want to predict what here? End of sentence. End of sentence, which is a special token here, or special word here. Okay? With that, of course, I can also, if the network is really well trained with so many examples, of course, the network will not be trained only on one example, right? It will be millions of examples. And we don't need any labeling here, right? This is just plain text. I will just train the network on plain sentences. I don't need to do any manual labeling, right? Just the sentences that will be the input to the network. So this is completely unsupervised. I mean self-supervised. Okay, we don't need any manual labeling. And with that also, we can compute the probability of the sentence. And actually, the network will learn to maximize that probability if the input is that sentence. Okay, so that's an idea of training a language model using a recurrent neural network. This idea is the core idea behind how we can get the contextual embeddings. Any question about this general idea? Okay. Then now let's talk about ELMO, which stands for embeddings from language models. So this is an extension of the previous idea, but here instead of having just one layer, one RNN layer, we have two, and we also have two RNNs, one to take the sentence from the left and the other from the right. Okay, so that we can have the context from both sides, not only the previous words, but I also will see also the next words, so that I can really learn from both sides. The previous network, if you noticed, we only look at the left context. Okay, here the idea is extended to have what we call bi-directional LSTM, or LSTM is a special type of RNNs. So this is bi-directional because we look at both directions, okay, the left direction and the right direction. And the input, as we also had in the RNNs, are the words. Now, when we say the input is the word, we know that neural networks are all about numbers, right? So we'll have to feed the network as an input some numbers. Where can we get the numbers for, or how can we represent words as numbers? Yes, we can use the one-hot encoding. Okay, we can use the one-hot encoding, or we can use static learned embeddings like word-to-vec or GLOB that we studied already before, right? So we can start by that, but the goal of this is to get contextual embeddings. And we start with the static embeddings for each word, but we learn new embeddings based on this specific sentence. That will be the input to the network. Of course, I have to first train this network with so many examples like what we saw in the previous slide, with so many sentences. And Then after that, after we are done with training the network to learn the language model, now we use the network, the trained network, to generate the embeddings. Okay, how? We will input the new sentence. Let's say that the new sentence now is the cat is happy. For each word, we will have the hidden state from the first layer and from the second layer. We combine them with the initial embeddings with some specific function. So it's a function over the three things will give us one vector, which will be now contextual embeddings, because it depends on this specific sentence. It's not static. Okay, and it's learned to maximize the language model, to maximize the likelihood probability of seeing this sentence. Okay. No, the embeddings will not be the same. The same for what? The size. The size is determined, of course, by the size of the hidden states in the network. So it will be fixed, of course, for all words. Yes, Paula? Okay, you mean this arrow in specific or this one? This one. Okay, so here that shows you how we will get the embeddings eventually. After we train the network, then in the inference time, when we want to get the embeddings for a new sentence, we input the sentence, and for each word, we get the hidden state from the first layer and the hidden state from the second layer. We combine it with the input embeddings with specific function. You can assume for now that this is the sum function, for example, just for simplicity. We'll add them together, and that will be the embeddings for every word. Now, this embedding, of course, depends on the entire sentence. It's not static. So if you change that sentence, if you change one word even in that sentence, you will get different embeddings for every word. Okay? Did you get it now, Paula? Yes. Oh, no. In the input, it is just the sentence. Here, we determine the end of the sentence by the tokens. The start and the end, actually, by special tokens. So this is a very high-level description of Elmo. Elmo is really made a breakthrough in the field by having this contextual embeddings. Before that, we had static embeddings that you can download and use as a lookup table. But now we can have embeddings that depends on the context of each sentence. Okay, so the word appearing in two sentences might get completely different embeddings. We can't. We can or we cannot. Why we cannot? Okay, so we can't use this. Of course we can. Of course, otherwise we wouldn't study it. But how? I think your question is how. How can we use this? Pre-trained embeddings, the ones that we studied in the previous lecture, we can download them, okay, and then just ask for the embeddings for the word happy, will give you the vector, right? So that's straightforward to be used. Here, how can we use that? How can we get these embeddings? Huh? Okay, let me modify this by saying that we need to use the pre-trained model. This network is already trained. Okay, so in the previous, in the pre-trained models, pre-trained embeddings, we download the embeddings, right? Here we will download the model and we use it to generate the embeddings given the sentence. Okay, so the model itself now you will use it. You use the neural network that is trained. Feed it with the sentence, it will give you the embeddings for each. Exactly. Yes, over. I think there is a limit, of course, but the limit is not very small. Embedding for each word. Yes. You can combine this, the embeddings of the words to the way you like. Any other questions? Is the idea here clear, that the basic idea? Umama, are you with us? Okay, we didn't talk about transformers yet. Stay tuned to next lecture. Okay, that's a different story. But in principle, yes, transformers are actually built after this. We are moving in time now. Now we are in 2018, by the way. Okay, with this model, I think Wortovec and Globe were 2013, 14, that range. Now we are in 2018. Next lecture, we will be at the end of 2018 when we talk about transformers and BERT. Any other questions? Okay, so we are done with term representation lecture. Any question from the guys online?
No, thank you.
Okay. Right, we'll switch gears now and talk about link analysis that was supposed to be discussed last week. Inshallah, it's a short topic, and then we will switch to a new topic, which is learning to rank. So what do we mean by link analysis? Here we are talking more about web search in particular. So far, we didn't talk much specifically about web search. We were talking about search in general, right? Searching any collection. Here we are more specific about a domain where pages are linked together. Okay, where do we see links on the web? Are pages actually on the web linked? How? With the hyperlinks, right? Each page has some hyperlinks. When you click on that hyperlink, you will go to another page, right? So this is like a link in the web graph. And if you view the web as a graph, graph has nodes and edges. The nodes will be the pages, and the edges will be the hyperlinks between the pages. Okay? So we have billions of web pages, but not all of them are at the same quality or same authoritativeness, okay, or informativeness. Not all of them are at the same importance, okay? And pages that are more important than others should have some priority in search, right? Somehow. Because they are more probably trusted or more reliable or more authoritative. So the idea here is that, or the problem here is that how we can use the links in the web to get better results. Or, in other words, maybe a simpler problem, how can we rank pages on the web based on their importance or based on their informativeness? One, and of course that can be used with within the ranking algorithm as we will see each other. That can also be viewed as popularity, any page that is authoritative or important will be popular. Okay? Or popularity is part of the notion of authority here, or informativeness here. Type. One idea is to count the number of in links. What do you mean by in links? Links that are going to the same page. And if a page has so many in links, so many pages are linking to that page, maybe we can say that this page is important. Right? Right. What is the problem with that? Imagine now that we found a page that has so many links, and we consider that page really important page or popular page, because you might think of it that way, right? It's popular because it has so many links, right? So many other pages, so many external pages are pointing to that page. Yes? Yes. Okay, yeah, so one page can have so many links, but these links come from unimportant pages, right? So that can happen, right? Also, if the importance or the popularity of the page is only defined by the inlinks, anyone can have his own page very popular that way, right? I can make dummy pages on the web and make them all point to my page. I can even auto-generate that, right? With thousands and maybe millions of pages. And all of them are pointing to me, then I will be the most important, most popular page on the web. Okay? Huh? Exactly. Exactly. Okay? So what the idea that I just mentioned is called spamming. Okay? This is like spam email is an email that is trying to trick you, right? To do something that is hidden somewhere. Spamming in the web also something like this. Doing something that will lead you to think that some pages are more relevant or more important than they should. Okay, so inlinks has this problem. So we'll need to find ways or techniques or algorithms that will be less affected by such behaviors. Okay, one of them that is really very common and very famous is called PageRank, and this is the algorithm that we will study today, Charlie. So what is PageRank? How many of you are familiar with PageRank? Okay, good. Fine. PageRank depends on a model called random surfer model. What does that mean? The model is as follows. We will start at one page, any page on the web, okay? And then we will find within that page one hyperlink, and let's say that the page has 5 hyperlinks. We'll select one of them randomly, and we click on it. What will happen? It will take us to that page, right? That is linked by this hyperlink. And then we repeat the same process. On the new page, we will select randomly one of the hyperlinks, and we click on it. We go to a third page, and then we go to a fourth page. And maybe from that fourth page, maybe we will return to the first one. And then we go to a fifth one, and so on. We'll do that infinitely. Infinitely. This is what we call random surfer model. Now, when we do that infinitely, we can, let's assume that we can count how many times each page on the web will be visited. How many times I will go to every page in the web. Okay? The visiting rate, which is the number of visits to each page over the total number of visits, is what we call PageRank. So PageRank is like the rate of visiting of a random surfer who is randomly surfing the web, going from page, jumping to another, using the hyperlinks. Okay? With one more addition to that, which is that at some page, the surfer might decide to randomly go to a completely different page, not necessarily linked by the hyperlinks of that page. And the server will do that with some probability, let's say 15%. So 15% of the time, the server will jump to a random page that is not necessarily linked by the current page, and 85% of the time will go to one of the linked pages. Okay? So that's now the complete model. If we do that infinitely, then each page will be visited with some frequency, and that rate of visiting each page will be PageRank. That's how the model works. Okay, that's how the model works. Yes. Of course, PageRank is computed offline. Given the graph, we'll see how it is computed. There are, of course, efficient ways of doing that. But that's the basic idea. Okay, that's the basic idea of random surfer model. Now, if the page is, let's now think about the meaning of that. If the page is highly visited, what does that mean? Why? It's not only many pages. It's that it was reachable from other important pages that are also reachable. Okay? Yani, one page is visited a lot. There are many factors here. Maybe it has many links, or maybe it has few links, but these links come from pages that are highly reachable, that are highly visited. Okay? So the idea here is that, and this is, by the way, a social notion. I am important if many important people know me, or even few important people know me, but maybe of high ranks. Okay? So I don't have to have, for example, so many friends. It's only sufficient to have a friend who is the maybe son of the king. I will be famous because of that, because I'm known by that person. Okay? So my importance comes from the importance of the pages that are linking to me, if I'm a page. Okay? So that's the idea of PageRank. Yes?
One page, like Al Jazeera website, linked to this page.
Yes, that's a very good question. Okay, of course, assuming that Al Jazeera is popular, okay, which I think is true, at least here. Now, if Al Jazeera is pointing to my page, then I will get some of the popularity of Al Jazeera, right? Because Al Jazeera is pointing to me, so I might be important also.
So
I will get some credibility, and this is like modeling the credibility. If Al Jazeera is credible, or trusted, or important, or popular, or high quality, pointing to it is like pointing. Al Jazeera pointing to me is like endorsement for me. Okay, it's like giving me some credit.
how can my page, the number of visiting my page be high?
Because many people, yes, first it's not only about the number of links, but the number of visits. Okay? Yes. Now, if Al Jazeera is popular, many people are visiting it, right? So many people also will visit me, or at least a good portion of them will visit me. So that's the idea. Okay? Any questions about the general idea here?
That's not related to weights. It's like is it my page? Does mean this one link for me, and this link has weight.
No. We'll see that. We'll see it is related. It is somehow related. Stay tuned. Any other questions? Fine. Let's see some details now. So this is explaining again the model. So we'll browse the web using the following algorithm with probability lambda. Okay, we will jump to a random page. This is called teleporting. Okay, so teleporting means jumping from the current page to completely random page. So you will not follow the hyperlinks within that page. We'll just jump, and we do that frequently, right? When do we do that? These two models, which is teleporting or following one of the links, we actually do in our daily use of the web, right? Sometimes we click on a page, sometimes we are on a page and we click on one link of that page to go to another page, or we can decide that, okay, we are done with that page, let's go to CNN to see the news, or to go to Al Jazeera, or go to my page, or go to somewhere else that has nothing to do with the current page, right? So this is called teleporting. And we assume that the probability of teleporting here is fixed, which is lambda. Okay? Usually lambda is 0.1, 0.15, 0.2, something like that. And the probability of clicking on a link on the current page is, of course, 1 minus lambda. Okay? Type. Once I decided which way I will go now, whether doing teleporting, which is going randomly, or clicking on a link on the current page, now I will, let's say that I decided to click on a link. Okay? Now, based on the number of links in that page, I will pick one randomly. So if I have 3 hyperlinks on the current page, then the probability of clicking on each one of them is 1 over 3. So if I have n links, then the probability of going over any one of them is 1 over n. But that's, of course, multiplied by the probability of 1 minus lambda, right? If I decided that way. That would be the total probability. And then we start again with the new page. So page rank of a page rank, by the way, is a score. And it is a probability. I mean, it's a score between 0 and 1, which is a probability of visiting that page using that model. So page rank of a page is the probability that the random surfer will be looking at that page, which is long-term visit rate. Okay, links from popular pages will increase the page rank of pages they point to, and we discussed that already. Any questions so far? Type. There is also a notion called dangling links. So there are some links, some pages that don't have links. It can happen, right? A page doesn't have any hyperlink. Okay, so that's one case. But this case in our model is solved, right? How? Because we can do the reporting, right? We can always jump to another completely random page. So we'll not be stuck in this case. So this case is already covered by the model. There are also some pages that contain only links that no longer point to other pages. There was a link, and we see that, right? Sometimes we click on the link and it doesn't go anywhere. Why is that? Yeah, the page that we are pointing to is deleted, is not reachable now. Okay? The link changed. So there are many ways. Still, also the teleporting will solve this, right? Because now we will not go to that page and we go randomly to another page. Some pages also, or some nodes in the graph, have links forming a loop, okay? And that the algorithm itself will deal with it. Okay? So again, we don't need to do anything. Links that point to the first two types, which are the pages that don't have links or the links that are broken, are called dangling links. So this is just a definition. Okay, so dangling links means links are not working, whether they don't exist or broken. Okay. And as we said in the second case, which was with links that are broken, it's not necessarily that these links are actually broken. The pages that are pointed to by that links don't exist. It might be the case that the crawler of the search engine didn't get it yet, or it's not indexed yet, so you will not be able to go to it. Okay. it's not code. It's not there yet. Okay? So that's why it will be also considered dangling links. It's not working anyway. Type. Now let's get into more detail into how the PageRank scores are actually computed. Forget now for a second about the teleporting case. Okay, let's think about the simplified case when we just go through the links. Okay, so assume that we have this simple graph. We have 3 nodes, A, B, and C, and you see the links here. Now, if I want to compute the PageRank of C, based on what we learned, PageRank of C is like the probability of reaching C, right? Right. The probability of reaching C depends on A and B, right? Because I can reach C through A, or I can also reach C through B, right? Since we ignored the dangling case, then we will stick to the case when we choose a link through the current page. So we'll not do any teleporting. It's just one of the links, one of the hyperlinks in each page. Okay? So to go from A to C, the only way is to choose one of the links of A. Right? How many links A has? 2, 1 to B and 1 to C, right? So what is the probability to go from A to C? If we given that we will go from A, 1/2, right? So that's why it is the probability of getting to A times 1/2. Plus, because there is another route by which we can get to C, right? Which is through B. Now B, how many links coming out of B? Just 1. So it will be just probability of B/1. So now that will be the probability of visiting C, which is the PageRank of C. Okay? So that's of course the simplified version in which we didn't use any teleporting. How can we generalize this? So we saw this on a very small example, right? But I think we can easily generalize this. We can say that probability of or PageRank of X, node X, okay, in general, okay, summation of summation over what first? Very good. So let's say that these are Y. So Y belong to in links of X, right? Okay, we'll call it in of X. Okay? Type. Then for each Y coming to X, what should we do? So PageRank of Y over what is N? Very good. So over number of out of Y. Out of Y here is the set of the nodes linked from Y, okay? And the determinant here means the cardinality is the size of that set. Okay, so do you understand the notation so far? Okay, that's it. Why did we divide by the number of out of Y? Because we choose one only. So this is like multiplying by 1 over this number. Okay, is that clear for everyone? Any question about this? Yes.
For example, C and B.
Yes.
So to get C, we need A and B.
Yes. Yes. We'll focus on that now. Next. Okay. So let's see what we have. So that's exactly the same equation that we got. Okay, summation over all. So B here is the set of pages that point to U. U is the X in our example, and V is Y. Okay, so summation of all the nodes pointing to U. So let me erase this then. Summation of all nodes pointing to U. Page rank of this node, of each of these nodes, over the out links of that node. Okay, that's exactly what we mentioned. Any question up to this point? Okay. Type. What is the problem here? What is the problem?
So, like, to get the page rank of
Yes.
one page, we need the page rank of others.
Why is that a problem?
Because they can depend on each other as well.
Okay, so here there is a dependency here. Page rank of U depends on the page rank of what? Of all the nodes that are pointing to U, right? And that's the logical meaning that we discussed earlier, right? My importance comes from people who are pointing to me. Type, why is that a problem? Everything is depending on the other right now, right? What is that called? Recursion. Exactly. Okay, so that's recursion. That's recursion. Okay, page rank of U depends on page rank of V, and if you computed page rank of V, probably you will find that at some point it will come back to U. Okay. No, it's not infinite, but it is recursive. It is recursive. Actually, I'm not sure if it's infinite or not, but it is recursive for sure. And there is no closed formula to solve it. When we have a recurrence relation like that, and there is no closed formula, how can we solve it? Of what? Okay, not exactly. Okay, copying the number of times, but we have to consider all cases. Okay, so we will do what the basic solution always with the recurrence relation that doesn't have closed formula is to do it iteratively. Okay, so we'll have an iterative algorithm to go through the graph and compute page rank, and we will stop at some point with an approximation. Of course, we will not get the exact page rank unless there is convergence, earlier convergence, but we'll have to stop at some point in the iterations over the graph. We will see that. Okay, but at least now you got the problem. The problem is that there is a recursion in the equations. Okay, so which means that there is mutual dependency. We'll have to break that dependency somehow. Type, to do an iterative solution, we'll have to start somewhere. So we'll have to know page rank values in the beginning. Okay, so we'll have to have an initial value, page rank value for each node, and then we compute the new values with the first iteration. We'll compute new values of page rank for all nodes, and then we'll compute a third version and fourth version and so on. So that's what we mean by iterative solution, right? As we do that more times, we'll get closer to the actual page rank score for every page. Exactly, yes. It will be updated over different iterations. Now, usually in the beginning, if it was not mentioned otherwise, we assume equal page rank for a page rank score for all pages. Okay, so if we have 3 pages, like the example, the toy example that we are using here, then each page will start with an initial value of 1/3. Okay, type. If that's the case, then what should we do? So we'll start with page rank equals 1/3. what will be the new value of PageRank of A? Tell me. Which will be? Yeah, tell me how we compute it. Look at the graph and tell me how we compute
Isn't
it.
that-
Like what we did in the previous example, right?
Yeah.
Muhammad?
Isn't that going to be 1 over 3 over 2 over 3?
1 over
understanding.
3. Why is it 1 over 3?
Because we only have C pointing back to A and we assume all are equal weights.
Okay, one
So
second.
that's 1 over
So
3.
we are computing PageRank of A, right? Who points to
Yes.
A? C.
C.
How many links out of C? 1. So it will be 1
Yeah.
over 3 times 1 over 1, just to be clear. So that will be 1 over 3. Type. Thanks, Muhammad. How about PageRank of... Are we done with PageRank of A? For that iteration, it's done. For that iteration, it's done. Okay? How about PageRank of B? Anyone? Raise your hand, please. Otherwise, I will point to someone. Tajida. 1 over 3 again? Why? So, who is pointing to B? A, right? Only A? Only A. Okay. So, it will be 1 over 3, which is the PageRank of A, divided by, multiplied by 1 over 2. Why? Yeah, because A has 2 links. So this is like distributing my current PageRank through the links coming out from me. Okay? And you see here, this is the PageRank of this page now is 1 over 3, right? But this page has 2 links out of it. So 1/2 of this value will go to B and 1/2 will go to C. Okay? So this is like distributing my PageRank over my outlinks. So this will be 1 over 3 times 1 over 2, and that's it? Okay, how about PageRank of C? Hera? So how do we compute PageRank? We look at the pages that are pointing to it, pointing to C now. What are the pages that are pointing to C? A and B. Is that right? A and B. Okay. Okay, one by one, please. Okay. Huh? Yes? Yes? No, times what? 1 over 1? Really? How many pages coming out of A? 2, right? Not 1. There's 1 here and there's 1 here, right? Right? So we should multiply by 1 over 2. Is that it? No, because we can reach C from B also. Okay, so it will be PageRank of B, which is 1 over 3 now, times. So now we are talking about B, right? B going to C only, so it will be 1 over 1. PageRank of A didn't change. PageRank of B changed it. PageRank of C changed it. Huh? What is that? There is something wrong here? Okay, I got your point. You want to use the current value of PageRank of B? No. In that iterative solution, we don't update until we finish everything. That's the first iteration. Now, let's go to the second iteration. And can you tell me what will be page rank of A in the second iteration? Can someone compute these, please? This is 1 over 6, right? And how about this one? 1 over 6 plus 1 plus 2 over 6, which will be 1 over 2, right? Okay. Do you notice? What is this? What are these? This is the priority distribution, right? That's priority distribution. Type. Now page rank of A in the second iteration, Anoud. 1 over 3. Why? Let me erase this. So we are now page rank of A. Which is page rank of what? We want to compute page rank of A, right? How do you compute page rank of A? We look at what pages are pointing to A. What pages are pointing to A here? Only C, right? Only C. So what is the page rank of C? Currently is 1 over 2. Right? So it's 1 over 2 divided by the number of links, outlinks of C, which is 1, right? So it's like multiplied by 1 over 1, which is half. What page rank of B? Of A, which is times, which is 2. So this will be 1 over 6. Type. One more time, and we'll stop it. So, page rank of C, Marina. Page rank of A, which is 1 over 3 times 1 over 2. Okay, plus. So that's from A, right? There's another path from B. So from B, page rank of B, 1 over 6. Oh, sorry. Multiplied by 1 over 1. Why is that? Because it's only 1. So what will this be? Total is 1. Any questions? So we went through how many iterations here? 2. Right? Of course, I can ask you in the next quiz, go in 10 iterations. Okay. Tell me page rank after 276 iterations of this specific node. Okay, in 20, no, 20 كتير. Just 15. Of course, yes, yeah, you are right. Of course, but we'll not discuss this here. This can be represented in a matrix vector multiplication, okay, and can be done much more efficiently. Of course, we are doing it this way just to show you how it is computed. Any questions? Type, what is missing here? Yes, Muhammad?
Yeah, just to confirm, that means this is why in Markov chains we also introduced the random factor as well, right?
Yeah. That's why that's exactly the next step. That's why we call this simplified case, by the way. What is missing here? The teleporting, right? Teleporting. So what should we add to account for that? Yes, we should multiply all of this by 1 minus lambda plus lambda. Lambda is the probability of going to any page, right? What is the probability of going to any page? 1 over n. N is the total number of pages. Okay, that's exactly the right formula. Okay, so that's what we did, and that will converge to these values at the end. So we'll get very close to these values. But now, if we want to add, so that's the actual page rank. We multiply everything we did with 1 minus lambda, and we add lambda over the number of pages, which is 3 here. So generally, we'll have something like this. This is what we saw previously, right? Multiplied with 1 minus lambda, and we add lambda over it. Sorry? No, this is just a constant, will be a constant. Typically, it is like that, but you can, in different applications, you can use different values. Of course, this is the basic page rank, right? There are variants of that, but that's the basic idea. Let me ask you, let's say that we computed page rank now for the entire graph. Okay? How is that related to IR? Where is the search here? طب where is the query here أصلا? Why did we waste our time here without even having any query? Yes, Muhammad?
I thought the whole idea behind PageRank is to order the retrieved documents more so than finding them, or am I incorrect?
Oh, only the retrieved documents? And you mean we will do retrieval first and then over the search results, let's say 20 documents, we will get PageRank?
At least that was my understanding.
Oh, no, that's not what we will do. Yes, Khawla? Okay, very good. So this score is called query independent score. The scores, the ranking scores that we discussed earlier in the course were query dependent, right? Given a query, give me a score for that document. Here there is no query. This is independent of any query. This is a static score. Okay, this is called query independent score. I can combine it with any query dependent score. There are many ways of combining it. One way that Khawla suggested is multiplying. Another way is adding with some weights. So we can add it to whatever retrieval score that is query dependent that we have. Okay. So this is how, or the second half of the core of the lecture today, when we talk about learning to rank, we'll see that that will be also used. Here is an example from Wikipedia. In this example, this is a small graph, but it shows you nice things. First, the scores or the PageRank scores are indicated in each node, and the size of the node is proportional to the score. Okay, so it doesn't mean that this node is really big. Okay, all nodes are the same, but the size here just to show you the PageRank score for it. Okay, so for example, this one has the highest PageRank score. This one has higher than those, and so on. Look at this and tell me what is interesting that you saw in this example. Yes, Khawla? Very good. C has only one link, only one in link, but it came from a page that seems to be very popular. Almost everyone is pointing to it, or many are pointing to it. So it gets some credit from that page. Okay, through just this one node. Okay, what else? Yes.
The 1.6 has the highest
No one is pointing to them. Yes? What else? Yes. Abdullah?
E is not as important as B because it's linked in non-important.
Yes.
cases.
Yes. If you look at the number of in links of E and B, maybe they are the same, or maybe E has more links. Okay, but the page rank eventually of E, the page rank of E eventually is much less than B. Why is that? Because it's pointed to by unimportant pages. Okay, very good. Any questions? Type one more thing. Okay, so PageRank actually was introduced by Google. Okay, it was an idea of two graduate students in I think 1998. That's really old idea. But this idea specifically was one of the key ideas that made Google that better than other existing search engines at the time. Okay, it was really a breakthrough in search, in web search, using this score, PageRank. Okay, it made really a big difference in the performance of search engines. At the time, by the way, the inventor of this algorithm were graduate students at Stanford, PhD students. They got their master from actually one at least of them, maybe both, I don't remember, but at least one of them got his master from the university from which I got my PhD, which is University of Maryland. And then they went for PhD at Stanford. They had this idea, and while they were at Stanford, when they found this idea really booming or very effective, they launched Google. They founded Google, okay, around 1999 or 2000. Did they continue their PhD? No, they didn't. No need, exactly. Okay, they didn't continue their PhD. خلاص يعني. We got what we want. Okay, so that was a nice lesson. PageRank is used, of course, but it's not the full story. But it is one of the very important features that Google is or was at least using in web search. Okay.
Doctor?
Yes, Muhammad.
I know it's a bit tangential, but I'm kind of curious. So how did exactly Google popularize MapReduce then?
Oh, MapReduce is completely different from this, Muhammad. Don't get us into MapReduce here. If you want,
Because I still remember the trace behind it. It's still scarring.
No. MapReduce has nothing to do with PageRank. MapReduce was introduced in 2005 or 5 years after PageRank. MapReduce was the technique that Google used to make the indexing and maybe computing PageRank scalable. Okay, but PageRank, of course, was before that. And if you are interested in MapReduce or such kind of techniques, you should have attended my big data class that is on Wednesdays, or you check the lectures on the web. And MapReduce, as I said, not MapReduce, PageRank, as I said, it's just one of the features or one of the key features that is used in web search. But it is used also with other features, and we will learn about that, inshallah, today when we talk about learning to rank. It is also useful not only for web search, but to know which pages the web search engines should crawl next. You know, web search engines like Google, they don't crawl or get copies of the pages once, because pages change over time, right? Okay, so frequently they do this crawling, and they need to prioritize which pages they get their content. Okay, so they use PageRank is is one of the factors that is used to prioritize the pages to be recrawled and thus re-indexed in web search engines. One last question. Why is it called PageRank? Because it's ranking the pages, right? Okay, it is called PageRank because one of the inventors is called Larry Page, not because it's ranking pages. Okay, this one is Larry Page, and this one is Sergey Brin. Those are the founders of Google. Because he was the first author, probably. I checked actually the paper today. It was really, actually, this paper, PageRank, bringing the order to the web, was the first ever paper that I read in the field of IR. I had no knowledge at all when I met my PhD advisor the first time in an interview, and I told him that the only paper that I read, the only thing that I know about IR was PageRank, because PageRank was really famous at the time, and I wanted to know why Google is that effective or that more effective than other search engines. Yes?
Once I read that also the PageRank account, as a company, I can pay for Google to put to.
Oh, no, that's another story. That's a different story. That's in the ads, right? That is related to ads, advertising. Okay? That's a different story.
No, I heard that it will give the page more score than others.
Not more score, but it will be shown in the advertising panel, but that's not PageRank.
Not only in advertising, even in ranking.
It's called SEO.
No, but that's spamming. That's like spamming, right? Like trying to trick computing PageRank.
They would know, but they would get the search engine itself. It's not.
Now, okay. Once people know now about PageRank, they will try to trick it, right? Try to make their pages in a way that will have high PageRank. We'll not discuss that. Okay. That's a different story.